In the previous video, we defined a function f of x, and it was just a polynomial. Now we'd like to do something a bit more complicated so that we can simulate or approximate derivatives, which we've been talking about for some weeks, using these tools in Python. So let's say def, this is defining a new function, and I will call this function dir for derivative. Let's call it derivative. Let's be more descriptive. And I can only take a derivative of something with respect to something else, so I will call the first thing x and the second thing t. So when we read this, it is dx dt, the derivative of x with respect to t. Remember, to enter the function, we need to have a colon, hit return, and notice that we're indented, so here we're inside the function. Now I've input 2. In my mind, I know that these are going to be arrays. So I might have a few hundred x values and a few hundred t values, and I want the derivative of one with respect to the other. I need to define a new array to put the result in. So my array will be called d for derivative, and I will define d to be np.zeros of the length of x. This ensures that the box we're putting data into has the right size, has the same size as x and t, and if we were being really careful, we might put in some checks to warn a user if they tried to take a derivative of x with respect to a t that wasn't the same size as x. But we're going to use this code ourselves and hopefully use it in the correct way, so we can worry about details like that later. Now remember, we used a midpoint rule to approximate the derivative in the past when we were working with Scratch and when we were working with Google Sheets. I know that I can approximate a slope at a given point by taking the value at the next point minus the value at the previous point for both the rise and the run. So how can we do that? We can use a for loop. We'll use the traditional name for a dummy variable, I, for index. For I in range, what is our range going to be? Well, remember that my left data point doesn't have a left neighbor because there's nothing to the left of the leftmost value in an array. So instead of going from 0, the leftmost value, to the end, we're going to go from 1 to the length of the array minus 1. Len of x minus 1. In that for loop, what are we going to do? D of I will equal the rise over run. So I'm going to put these parentheses in so that my division is occurring without error, thinking of my order of operations carefully before I begin. Now I will take x of I plus 1 minus x of I. Notice that I'm using square braces here to address a value in an array. This is the I plus first element of the input array x. And we're going to subtract x of I minus 1. And I always like to copy and paste instead of typing if I can. It helps me avoid errors. So here we're going to have t of I plus 1 minus t of I minus 1. So you might notice we did this for elements 1 through the end minus 1. That means I have not taken care of the 0th element of this array or the final element of the array. So I would like to handle those boundaries, those endpoints. I will say that d of 0, just to fill it in for now, will be the same as d of 1. This is not a perfect thing to do, but it's better than just having it be still 0, which was the value we initially set for each element of this array. Similarly, d of the last endpoint will be the same as d of the second from last endpoint. So we're just setting each of those values equal to the value next to it. Finally, this derivative function will just return that new array, d. Remember, to escape out of this function, I need to hit backspace so that I'm unindented. I verify visually here that I'm lined up with def, none of the indented work. Oh, notice here, I'm glad I checked that my return does not need to be inside my for loop. So I've unindented once, undented. I'm outside the for loop, but inside the function. To see if this is working, let's make a new array. I'll call it Vx. Vx will equal the derivative of x with respect to time. So let's say Vx equals derivative, calling the function we just wrote, of x versus t. To see what that looks like, let's come back here. Notice we have a few lines of code here where we plotted x versus t and y versus t. I'm just going to duplicate those, so I'll copy those lines here and come down to a new cell, my newest cell, and let's plot x versus t and then our new quantity Vx versus t, and this should let us see what the x position is doing versus time and how quickly that's changing. Let's take a look, hit the play button, and I can see that my x versus t looks like a sine function in green, and my Vx versus t looks like what I know the derivative of sine is, which is cosine. So this seems to be working. I'm sure you have questions about this procedure, so please follow along the video and see what trouble you run into, and let me know when you get stuck or what you have questions about, and we will practice with this more on some of our real data sets in the upcoming problems and projects that we're working on.